A chemical formula is a way of expressing information about the proportions of atoms that constitute a particular chemical compound, using a single line of chemical element symbols, numbers, and sometimes also other symbols, such as parentheses, dashes, brackets, commas and plus and minus signs. These are limited to a single typographic line of symbols, which may include subscripts and superscripts. A chemical formula is not a chemical name, and it contains no words. Although a chemical formula may imply certain simple chemical structures, it is not the same as a full chemical structural formula. Chemical formulas can fully specify the structure of only the simplest of molecules and chemical substances, and are generally more limited in power than are chemical names and structural formulas. The simplest types of chemical formulas are called empirical formulas, which use letters and numbers indicating the numerical proportions of atoms of each type. Molecular formulas indicate the simple numbers of each type of atom in a molecule, with no information on structure. For example, the empirical formula for glucose is CH2O, while its molecular formula is C6H12O6. Sometimes a chemical formula is complicated by being written as a condensed formula, which conveys additional information about the particular ways in which the atoms are chemically bonded together, either in covalent bonds, ionic bonds, or various combinations of these types. This is possible if the relevant bonding is easy to show in one dimension. An example is the condensed molecular chemical formula for ethanol, which is CH3CH2OH or CH3CH2OH. However, even a condensed chemical formula is necessarily limited in its ability to show complex bonding relationships between atoms, especially atoms that have bonds to 4 or more different substituents. Since a chemical formula must be expressed as a single line of chemical element symbols, it often cannot be as informative as a true structural formula, which is a graphical representation of the spatial relationship between atoms in chemical compounds. For reasons of structural complexity, there is no condensed chemical formula that specifies glucose. Linear equivalent chemical names exist that can and do specify any complex structural formula, but such names must use many terms, rather than the simple element symbols, numbers, and simple typographical symbols that define a chemical formula. Chemical formulas may be used in chemical equations to describe chemical reactions and other chemical transformations, such as the dissolving of ionic compounds into solution. While, as noted, chemical formulas do not have the full power of structural formulas to show chemical relationships between atoms, they are sufficient to keep track of numbers of atoms and numbers of electrical charges in chemical reactions, thus balancing chemical equations so that these equations can be used in chemical problems involving conservation of atoms and conservation of electric charge. Overview. A chemical formula identifies each constituent element by its chemical symbol and indicates the proportionate number of atoms of each element. In empirical formulas, these proportions begin with a key element and then assign numbers of atoms of the other elements in the compound, as ratios to the key element. For molecular compounds, these ratio numbers can all be expressed as whole numbers. For example, the empirical formula of ethanol may be written C2H6O because the molecules of ethanol all contain 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. Some types of ionic compounds, however, cannot be written with entirely whole number empirical formulas. An example is boron carbide, whose formula of CBN is a variable non-whole number ratio with N ranging from over 4 to more than 6.5. These types of formulas are variously known as molecular formulas and condensed formulas. A molecular formula enumerates the number of atoms to reflect those in the molecule, so that the molecular formula for glucose is C6H12O6 rather than the glucose empirical formula, which is CH2O. However, except for very simple substances, molecular chemical formulas lack needed structural information, and are ambiguous. For simple molecules, a condensed formula is a type of chemical formula that may fully imply a correct structural formula. For example, ethanol may be represented by the condensed chemical formula CH3CH2OH, and dimethyl ether by the condensed formula CH3OCH3. These two molecules have the same empirical and molecular formulas, but may be differentiated by the condensed formulas shown, which are sufficient to represent the full structure of these simple organic compounds. Condensed chemical formulas may also be used to represent ionic compounds that do not exist as discrete molecules, but nonetheless do contain covalently bound clusters within them. These polyatomic ions are groups of atoms that are covalently bound together and have an overall ionic charge, such as the sulfate SO4 ion. Each polyatomic ion in a compound is written individually in order to illustrate the separate groupings. For example, the compound dichlorine hexoxide has an empirical formula ClO3, and molecular formula Cl2O6, but in liquid or solid forms. This compound is more correctly shown by an ionic condensed formula ClO2 plus ClO4 which illustrates that this compound consists of ClO2 plus ions and ClO4 ions. In such cases, the condensed formula only need be complex enough to show at least one of each ionic species. Chemical formulas as described here are distinct from the far more complex chemical systematic names that are used in various systems of chemical nomenclature. For example, one systematic name for glucose is -2,3,4,5,6-pentahydroxyhexanol. This name, interpreted by the rules behind it, fully specifies glucose's structural formula, but the name is not a chemical formula as usually understood, and uses terms and words not used in chemical formulas. Such names, unlike basic formulas, may be able to represent full structural formulas without graphs. Simple empirical formulas. In chemistry, the empirical formula of a chemical is a simple expression of the relative number of each type of atom or ratio of the elements in the compound. Empirical formulas are the standard for ionic compounds, such as CaCl2, and for macromolecules, such as CO2. An empirical formula makes no reference to isomerism, structure, or absolute number of atoms. The term empirical refers to the process of elemental analysis, a technique of analytical chemistry used to determine the relative percent composition of a pure chemical substance by element. For example, hexane has a molecular formula of C6H14, or structurally CH3CH2CH2CH2CH2CH3, implying that it has a chain structure of 6 carbon atoms, and 14 hydrogen atoms. However, the empirical formula for hexane is C3H7. Likewise, the empirical formula for hydrogen peroxide, H2O2, is simply HO expressing the 1-to-1 ratio of component elements. Formaldehyde and acetic acid have the same empirical formula, CH2O. This is the actual chemical formula for formaldehyde, but acetic acid has double the number of atoms. Molecular formulas. Molecular formulas indicate the simple numbers of each type of atom in a molecule of a molecular substance. They are the same as empirical formulas for molecules that only have one atom of a particular type, but otherwise have larger numbers. An example of the difference is the empirical formula for glucose, which is CH2O, while its molecular formula is C6H12O6. For water, both formulas are H2O. A molecular formula provides more information about a molecule than its empirical formula, but is more difficult to establish. Condensed formulas in organic chemistry implying molecular geometry and structural formulas. The connectivity of a molecule often has a strong influence on its physical and chemical properties and behavior. Two molecules composed of the same numbers of the same types of atoms might have completely different chemical and/or physical properties if the atoms are connected differently or in different positions. In such cases, a structural formula is useful, as it illustrates which atoms are bonded to which other ones. From the connectivity, it is often possible to deduce the approximate shape of the molecule. A condensed chemical formula may represent the types and spatial arrangement of bonds in a simple chemical substance, though it does not necessarily specify isomers or complex structures. For example, ethane consists of two carbon atoms single bonded to each other, with each carbon atom having 3 hydrogen atoms bonded to it. Its chemical formula can be rendered as CH3CH3. In ethylene there is a double bond between the carbon atoms, therefore the chemical formula may be written CH2CH2, and the fact that there is a double bond between the carbons is implicit because carbon has a valence of 4. However, a more explicit method is to write H2C equals CH2 or less commonly H2C, CH2. The two lines indicate that a double bond connects the atoms on either side of them. A triple bond may be expressed with 3 lines or pairs of dots, and if there may be ambiguity, a single line or pair of dots may be used to indicate a single bond. Molecules with multiple functional groups that are the same may be expressed by enclosing the repeated group in round brackets. For example, isobutane may be written 3CH. This condensed structural formula implies a different connectivity from other molecules that can be formed using the same atoms in the same proportions. The formula 3CH implies a central carbon atom connected to one hydrogen atom and 3 CH3 groups. The same number of atoms of each element may be used to make a straight-chain molecule, butane. CH3CH2CH2CH3. Chemical names in answer to limitations of chemical formulas. The alkene called butene has 2 isomers, which the chemical formula CH3CH equals CH3 does not identify. The relative position of the 2 methyl groups must be indicated by additional notation denoting whether the methyl groups are on the same side of the double bond or on the opposite sides from each other. Such extra symbols violate the rules for chemical formulas, and begin to enter the territory of more complex naming systems. As noted above, in order to represent the full structural formulas of many complex organic and inorganic compounds, chemical nomenclature may be needed which goes well beyond the available resources used above in simple condensed formulas. See IUPAC Nomenclature of Organic Chemistry and IUPAC Nomenclature of Inorganic Chemistry 2005 for examples. In addition, linear naming systems such as International Chemical Identifier allow a computer to construct a structural formula, and simplified molecular input line entry system allows a more human-readable ASCII input. However, all these nomenclature systems go beyond the standards of chemical formulas, and technically are chemical naming systems, not formula systems. Polymers in condensed formulas. For polymers in condensed chemical formulas, parentheses are placed around the repeating unit. For example, a hydrocarbon molecule that is described as CH350CH3 is a molecule with 50 repeating units. If the number of repeating units is unknown or variable, the letter N may be used to indicate this formula. CH3NCH3. Ions in condensed formulas. For ions, the charge on a particular atom may be denoted with a right-hand superscript. For example, Na+ or Cu2+. The total charge on a charged molecule or a polyatomic ion may also be shown in this way. For example, H3O+ or SO42-. For more complex ions, brackets are often used to enclose the ionic formula, as in B12H12 which is found in compounds such as Cs2, B12H12. Parentheses can be nested inside brackets to indicate a repeating unit, as in Co6, 3+. Here 6 indicates that the ion contains 6 NH3 groups, and encloses the entire formula of the ion with charge +3. Isotopes. Although isotopes are more relevant to nuclear chemistry or stable isotope chemistry than to conventional chemistry, different isotopes may be indicated with a prefixed superscript in a chemical formula. For example, the phosphate ion containing radioactive phosphorus 32 is 32PO43-. Also, a study involving stable isotope ratios might include the molecule 180160. A left-hand subscript is sometimes used redundantly to indicate the atomic number. For example, 802 for dioxygen, and 16802 for the most abundant isotopic species of dioxygen. This is convenient when writing equations for nuclear reactions, in order to show the balance of charge more clearly. Trapped atoms. The AD symbol indicates an atom or molecule trapped inside a cage but not chemically bound to it. For example, a Buckminster fullerene with an atom would simply be represented as MC60 regardless of whether M was inside the fullerene without chemical bonding, or outside, bound to one of the carbon atoms. Using the AT symbol, this would be denoted M at C60 if M was inside the carbon network. A non-fullerene example is, as at Ni12 is 23-, an ion in which one as atom is trapped in a cage formed by the other 32 atoms. This notation was proposed in 1991 with the discovery of fullerene cages, which can trap atoms such as La to form, for example, La at C60 or La at C82. The choice of the symbol has been explained by the authors as being concise, are readily printed and transmitted electronically, and the visual aspects suggesting the structure of an endohedral fullerene. Non-stoichiometric chemical formulas. Chemical formulas most often use integers for each element. However, there is a class of compounds, called non-stoichiometric compounds, that cannot be represented by small integers. Such a formula might be written using decimal fractions, as in Fe 0.950, or it might include a variable part represented by a letter, as in Fe 1xo, where x is normally much less than 1. General forms for organic compounds. A chemical formula used for a series of compounds that differ from each other by a constant unit is called general formula. Such a series is called the homologous series, while its members are called homologues. For example, alcohols may be represented by CnHOH Hill system. The Hill system is a system of writing chemical formulas such that the number of carbon atoms in a molecule is indicated first, the number of hydrogen atoms next, and then the number of all other chemical elements subsequently, in alphabetical order. When the formula contains no carbon, all the elements, including hydrogen, are listed alphabetically. This deterministic system enables straightforward sorting and searching of compounds.